So far we have started to learn about one function of two random variables and so on, and we have discussed about circularly symmetrical random variables. Now in this video we want to discuss about maximum and minimum functions. In other words, we have a pair of random variables x and y, and then we want to have the distribution of maximum of x and y or minimum of x and y. So let's say these are two new random variables. So the maximum and minimum functions, if you want to calculate that, suppose that if you want, for instance, maximum, so let's say z is equal to maximum of x and y. So if we want to find the CDF of z, so let's say fz of z, this is basically probability that z is smaller than or equal to z. And this means that the maximum of x and y is smaller than. So it's probability that maximum of x and y is smaller than or equal to z. And this means that if maximum of them is smaller than z, both of them should be smaller than z. So that means that probability that x is smaller than or equal to z, and this common means and or intersection or and. So they are the same. And y is smaller than or equal to z. So obviously this is the joint CDF of x and y, fx, y of at point z, and y also at point z. So if you have the joint CDF, you can quickly find the distribution of the maximum. For minimum, you could have same approach, and you can get this distribution. So you could quickly get from the joint CDF, you can get the CDF of the maximum and the CDF of the minimum. So you could argue that this is the area, the red area is dz, and this blue area is dw. So if you want w to be smaller than these, that means that your pair of random variables x and y should be inside the blue. And if you want z be smaller than or equal to z, that means that the pair of x and y should be inside this red area, which leads to this probability, and this one leads to this probability. So the maximum and minimum functions, if they are independent, if x and y are independent, because in the previous slide we found that fz of z was equal to fx y of z and z. So if they are independent, this function decomposes into a function of only the first argument, which is going to be fx of z, and the second one f y of z. So for the independent random variable, just you multiply the marginal CDF, you get the distribution of the maximum. Similarly, you can get it for the, if you get the derivative with respect to x, so it's going to be derivative of these times this one, and then derivative of these times this one, which is going to be derivative of these is the PDF times CDF, and then is going to be CDF times PDF of the other one. So we could. So if you multiply PDF of one random variable times CDF of the other one, and add CDF of the first one times PDF, the sum is going to be the PDF of the maximum. So this is always a valid PDF, provided that this is PDF and this is its CDF, this is PDF and it is CDF. So you could do similarly for the minimum and get this expression. So this is the complementary, CDF of W. So 1 minus CDF is called complement and is equal to probability that W is bigger than W. So it's got to be like probability of W is smaller than or equal W, complement of this event. So this is why we call it complementary. So the complementary CDF of the minimum is equal to 1 minus is complementary CDF of X times complementary CDF of Y. So here we had the CDF is equal to CDF times CDF. Here the complementary CDF is equal to complementary CDF. So if I denote the complementary CDF by F bar of, let's say, W is equal to Fx of X bar times F Y bar. So complementary CDF is equal to the product of the complementary CDFs, provided that they are independent. Similarly, by taking the derivative from here, I get this expression, which is longer than this one, but it's basically the PDF is equal to PDF of these times complementary CDF of the other one, and CDF, complementary CDF of the other one times PDF of this one. So these could be easily generalized into more than two random variables. So maximum function means that from the sample space, you have one function which gives you X, another function which gives you Y, and then here you select the maximum. So this is, and then we aim to find a distribution of Z from the joint distribution of X and Y. So, so we have written this expression, and then we got this one. So so if they are independent, this is the product. So I'm reviewing this, and we had this expression. For instance, if you have two exponential independent, the two independent exponentially distributed random variables with parameter lambda, the PDF of the maximum you could plug in. So here you have an exponential function, you have 1 minus e to the power minus lambda x, etc., and you replace it and you get the expression. So so quickly you can get this expression. So the maximum of two exponentially distributed random variables with the same parameter will have this distribution. So if this is the distribution of X, also distribution of Y, and if they are independent, you see that the distribution of the maximum is like that. So it's like here, this is smaller, but here the PDF of the maximum is bigger. So your distribution is pushed to the right. So this area is moved into this area. So let me clean up. So this area that is eliminated from here is replaced by this area, the upper one. Because if you take maximum of two random variables, the maximum is always bigger than each of them. So this is why a portion of distribution from here is moved to the larger values. Remember that the maximum is not a gamma random variable. So if you have a maximum of n random variables, so you could easily generalize the distribution you had, because if you say Zn is maximum of n random variables, so Zn is smaller than or equal Z means that maximum of all of them is Z. That means that all of them should be smaller. So it's going to be the intersection of this one. So this event is equal to this one. So, and because they are independent, probability of their intersection is product of their properties. So you could say that f Zn of Z is equal to product of over k equal 1 to n of f xk of Z. So just you replace all of those values of x1, x2, etc. by Z, and then multiply them together. So now you can calculate the derivatives if they are independent. And then, so to take the derivative, I prefer to take log. So if I take log that, I get fz of Z. And then this becomes summation over k equal 1 to n of log of f xk of z. Now you can take the derivative, so this will become f z of z, the PDF divided by the CDF, f z of z, becomes summation of the ratio of the PDFs, f xk of z divided by f xk of z, k equal 1 to n. Now if you want this one, multiply both sides by the CDF of f z of z, so kind of like you have this one, because this is f z of z. So this expression is what we get. Remember that if any of them is 0, so this you will have 0 divided by 0. So in those areas you have a maximum n random variables. So suppose that they are all independent with identical CDF of fx of x. In that case, you get these expressions. So now you can calculate derivative of that, and then you get this distribution. For instance, in this example, if this guy fx of x, if this is exponential, now you can replace it, and then you get this distribution.